Hello, class! I hope you all have a better understanding of vectors now. One of my favorite sections of physics is projectile motion. When you think about it carefully, projectile motion is motion in two dimensions. An object launched in the air at an angle is moving in the x direction and y direction at the same time. Here's a closer look of an example to what I mean by an object moving in the x direction and y direction at the same time. In this example, the ball is rolling off the table and another ball is dropped from the table's edge at the same time. The solid green arrows you see at each snapshot of the ball shows the direction of the ball's path, and the length represents the magnitude of the ball's velocity. Notice how the magnitude of the velocity increases because of acceleration due to gravity. Now let's focus on the green dash arrow for the x direction only. The velocity in the x direction is only represented for the ball rolling off the table because the drop ball has no motion in the x direction. Take a close look at the magnitude of the velocity in the x direction for the ball rolling off the table. What do you notice? That's right, the magnitude is the same throughout the entire motion. Let's think about this. You roll a ball off the table. We know gravity is pulling the ball down faster in the y direction, but what's affecting the x direction? We're ignoring any drag that might be caused by air. There's no friction from the table to cause the ball to slow down. So nothing. Nothing is causing the ball to slow down or move faster in the x direction until it hits the ground. Since nothing is changing the ball's velocity once it leaves the table, the magnitude remains the same throughout the entire motion. Now let's take a closer look at the velocity in the y direction. The result we see with the magnitude lengthening is expected because of the acceleration due to gravity. Last observation. Let's take a closer look again at the solid green arrow. Notice how the x and y vectors with the ball rolling off the table are the components for that solid green arrow. So the solid green arrow represents the velocity and actual path of the ball, and the dashed lines represent the components for the resultant velocity vector. I lied. One more observation. Again, both balls are dropped at the same time. Notice how the velocity in the y direction occurs at the same time with the same magnitude in both situations. Here's another visual snapshot showing that both objects let go at the same time. Even though one is dropped and the other has some velocity in the x direction. They both fall at the same rate in the y direction. Let's see if you can answer exercise C. Two balls have different speeds rolling off the edge of a horizontal table at the same time. Which hits the floor sooner, the faster ball or the slower one? They both hit the floor at the same time because they both move in the y direction at the same rate due to the acceleration of gravity. Now in the x direction, the faster one will move further in the x direction along the floor. Here is a diagram showing a ball launched at an angle from the ground. The solid green vector is the resultant velocity of the ball traveling, and the dashed lines are its components. Notice how the velocity in the x direction stays the same throughout the entire motion. Then notice how the velocity in the y direction decreases as the ball travels up towards the maximum height. At the maximum height, the velocity in the y direction is 0. But remember, the velocity in the x direction is not 0. As the ball travels downward, the velocity in the y direction increases. Take a closer look at how the velocity in the y direction at the same height is equal but opposite direction. Another similar feature is the launch angle equals the landing angle. Where does Apple land? A child sits upright in a wagon which is moving to the right at a constant speed. The child extends her hand and throws an apple straight upwards, while the wagon continues to travel forward at a constant speed. If air resistance is ignored, will the apple land in the wagon? Because the apple and the wagon have the same constant velocity in the x direction. If we ignore air resistance and friction, nothing will slow the apple or wagon. The velocity in the x direction will remain constant throughout its entire motion. A small heavy box of emergency supply is dropped from a moving helicopter at point A, as it flies at a constant speed in a horizontal direction. Which path in the drawing below best describes the path of the box as seen by a person standing on the ground? Ignore air resistance. D. Because if we ignore air resistance, the box will move at the same speed in the x direction as a helicopter until it hits the ground. And of course, it will fall with the acceleration of gravity. Recall, here are the kinematic equations we use for the x direction and free fall. But now we have an object moving in the x and y direction at the same time. For projectile motion, you need both set of kinematic equations for solving problems. However, the nice part is that the velocity in the x direction is constant. So what does that mean for the acceleration in the x direction? That's right, it's 0. So the kinematic equations are reduced, and you're really only left with x equals x naught plus vx naught t. And look at the velocity in the x direction. Since it's constant, that means the initial velocity equals the final velocity in the x direction only. So we can get rid of the last equation. And what variable do you notice that's similar between the kinematic equations in the x and y direction? That's right, time. If you happen to calculate time in the x direction, you can use that same value in the y direction. That's because the two velocity components in the x and y direction travel together for an object in projectile motion. Last set of equations you'll need for projectile motion is the velocity components in the x and y direction. With a given launch angle and velocity, you can find its components through trigonometry, because remember, components form right triangles. Now I think we're ready for our first example. A movie stunt driver on a motorcycle speeds horizontally off a 50-meter high cliff. How fast must a motorcycle leave the cliff top to land on the level ground below 90 meters from the base of the cliff where the cameras are? Of course, ignore air resistance. First step, write out our givens and what we're finding. So we know the initial height is 50 meters. The final height is 0 because it hits the ground. The final position in the x direction is 90, so we'll assume the initial position in the x direction is 0. And the initial velocity in the y direction is 0 because it's moving horizontally off the cliff. And we're trying to find the initial velocity in the x direction. Which equation do you think would help us find the initial velocity in the x direction? That's correct. X equals x naught plus vx naught t. Uh-oh. Which variable do we not know? Correct. We don't know time. Do you remember what we can do to solve for time? Yes, that's correct. Use a projectile kinematic equation in the y direction to solve for time, because we're given information about the y direction. Now cancel out everything that equals 0. Simplify the equations. Then rearrange the equation to solve for time. Plug and chug, and we get 3.19 seconds. Then rearrange the top equation to solve for the initial velocity in the x direction so that we get position over time. Plug and chug to get our final answer of 28.2 meters per second as the initial horizontal velocity off the cliff. Next example. A kicked football leaves the ground at an initial angle of 37 degrees with a velocity of 20 meters per second. Assume the ball leaves the foot at the ground level and ignore air resistance. We're going to calculate the maximum height, time travel for the football to hit the ground, and how far it hits the ground away. However, with our givens, we have the initial angle is 37 degrees, the initial velocity is 20 meters per second, we'll assume the initial height is 0, and at the maximum height, what's the velocity in the y direction? That's correct, it's 0, and we're trying to find the maximum height, or the final height. However, with our givens, it's more useful to know the velocity components in the x and y direction, since all of our kinematic equations have our velocities in either x or y direction. Recall, we can use trigonometry to find the initial velocity in the x and y direction. Plug in our values, and we get 16 meters per second and 12 meters per second, respectively. Now we can just replace these components as our givens instead. So which equations do you think we should use to solve for the maximum height? That's right. Vy squared equals Vy naught squared minus 2g times y minus y naught. Now cross out any variables that equal 0. Simplify the equation. Rearrange it to solve for the maximum height. Plug and chug, and we get 7.35 meters as our maximum height. Next example, the time of travel before the football hits the ground. Our givens now have some final velocity in the y direction that we don't know, and the final height of 0. And of course, we're trying to find time. Which equation do you think we should use? Correct again. Y equals y naught plus Vy naught t minus 1/2 gt squared. Cross out any variables that equal 0. Simplify the equation. Look what else cancels out. Time. Now the equation is reduced even further. Rearrange the equation to solve for time. Plug and chug, and we get 2.45 seconds for the football time of flight in the air. Now the next problem is how far away it hits the ground. For our givens, we can use time that we just solved, and we'll assume the initial position is 0. Which equation should we use? Correct. X equals x naught plus Vx naught t. Cross out the initial position. Simplify the equation. Plug and chug, and we get 39.2 meters for the total range of the football. Last two questions. The velocity vector at the maximum height and the acceleration vector at the maximum height. At the maximum height, our final velocity in the y direction is set to 0. To find the velocity vector, we need to break it up into its component at the maximum height. Well, we know the velocity in the y direction is 0 at the maximum height, and the velocity in the x direction never changes. So it equals 16 meters per second. If we were to use Pythagorean theorem to solve for the resultant velocity vector, we would get 16 meters per second, and we know it's in the positive x direction. Okay, last question. The acceleration vector at the maximum height. Again, we need the acceleration components at the maximum height. We know that the acceleration in the x direction is always 0, and the acceleration in the y direction is always negative gravity, or negative 9.8 meters per second squared. So the resultant acceleration at the maximum height is negative 9.8 meters per second squared, and referring to the negative y direction.